Uh, I'll be talking about techniques for IDE-friendly compiler construction and its application in blockchains. Okay. These are the content. Okay, just before we proceed, would like to quote this. So many textbooks are hard to understand, not because the subject is difficult, but the author can't remember what it's like to be a beginner. And I think compiler is one of those fields where authors like authors of Dragon Book, may seem that the subject is tedious and impenetrable, but you can get hang of it. I was nervous making this joke given the number of academics in the room. So apologies if anyone is offended. Just for those who don't know Dragon Book, there were previous slides in which a lot of people said textbooks optimizations. It's probably the Dragon Book textbook they are talking about. Okay. Okay. So whatever I'll be discussing is my experience in building a compiler for my current organization, Weilliptic. We are, as Professor Manas told, is a blockchain and AI-based stealth startup. And yeah, we are engineer-first startup, so we tend to do a lot of stuff of ground up, including the WIDL compiler, which I'll be talking about. Okay. So what are IDE-friendly compilers and why you should know about them? Okay. So for example, take this instance about this, let's say VS Code extensions you have, right? You get auto suggestions and IntelliSense in the editor. How it's a great productivity tool, right? But how they are built? The answer is LSP, Language Server Protocol. Okay, and language server protocol powers these IntelliSense in your editors. Okay, modern editors like VS Code or Atom or NeoVim for that matter. Now, what problem LSP solves is in pre-LSP phase. If you want to support a programming language in, let's say, n editors, you have to write support for those n editors. So you kind of have to implement the IntelliSense features n times. Okay. Now with LSP, your editor acts as a client and it sends you these editor events, which I'll show you in a bit, but these are events which sends you text buffers, text edits. And there is a single LSP server running in the background, and it just interacts with your client and gives you all sorts of diagnostics like go to definition, completion, diagnostics, and whatnot. All the features you love about an editor. Developer tool is basically your editor, and language server is the LSP implementation of a programming language, and these are the kind of events editor sends. For example, did open, did change, publish diagnostics, and so on. So all of these events are sent by the editor, and LSP have to understand that text somehow to give useful diagnostics. And that's where compilers would come into picture, because compilers are really great in reading a raw text and making sense out of it, okay, programmatically. So LSP uses compiler front-end specific phases like lexing, parsing, semantic analysis to handle editor requests, and then publish diagnostics and other IntelliSense features like go to definition, renames. This whole setup is called compiler as a service. And anyone who wants to learn more about it, there is an amazing talk by Anders Hillsberg in .js in which he talks about compiler as a service in TypeScript compiler. By the way, he is also the creator of TypeScript, C#, Delphi, Turbo Pascal, and he is an amazing person in the space. So now why it deserves a separate talk, or like what are the techniques, new techniques which should be introduced in making these IDE-friendly compilers, and what the CLI compilers lacked basically. So the most basic difference is in editor, your code is always broken, right? The programmer is always in process of writing code, so it's always syntactically broken, okay? But we even need IntelliSense features to work even on your broken code, okay? Now conventional CLI compilers are not great at handling this. They just bail out on the first syntax error they encounter, or maybe they have some recovery mechanism, but that also survives only up till the parsing phase, and they don't just move to semantics phase and gives you all sorts of type checking even though the code has syntax errors. And that's where there are few things you need to change in your compiler construction to make that work. Now the top two things you need while implementing your compiler is, one, it should be error tolerant parsing, also called resilient parsing. And the second thing is incremental parsing. Incremental parsing is kind of an optimization. The basic ingredient in making this work is an error tolerant parsing, and I'll explain what error tolerant parsing means. So roughly, the parsing never fails. Even if it has syntax error, it should never fail. Okay, parser always produces an AST, does not matter if there are syntax errors. Okay, so if you see the, for example, that result of a parser, it should not be either AST or diagnostics. It should be AST and diagnostics. Okay, and how you do that? Okay, so just a side note, Roslyn was one of the first softwares to do this kind of thing, to do this sort of compiler-based APIs. And again, Anders Zinzerberg was one of the main players in that. Okay, so error tolerant parsing is very simple in its core. If you see this expect function of parser, the expect function is the atomic parsing function. Anyone who has written compilers know that this is the atomic unit of a parser, right? You pass a token kind you expect, and then you get the result. Now conventionally, you either get a error or you get your token node back, an AST node. But in error tolerant parsing, as I told you, it never fails, right? So you see the first condition, if it matches the kind you are expecting, it returns you an OK token node. But let's say if it fails, it logs the error in the errors attribute on line 68, and then it returns a token node which accounts for the missing token there. So it goes forward and returns you an AST node. It's just the AST node variant is a missing token and not a valid token. Okay. Now if you have done this, you always get an AST back. And if you have an AST, you can move forward in doing all sorts of semantic analysis phase like name resolution, type checking. Anytime you encounter a missing token, you just ignore it. For example, if you encounter a missing token in declaration, you don't even feed it into your symbol table, let's say. Okay, so it's simple, that simple. And the second ingredient is incremental parsing. So incremental parsing is a kind of optimization which says that, okay, you already have an old AST, okay, and you have text edits. Why not to build the new AST by reusing old AST nodes and memoizing some of the parsing results so that only text edits can give you the new AST. Okay, so this technique is incremental packet parsing, really very famous parsing algorithm. Packet parsing key ingredients is that you basically memoize intermediate parsing results and reuse them. Okay, so anytime you reparse, you check in your memoization table. If it is there, you just return your AST node. Okay, obviously you have to take into account the text shifting due to the edit, but it's doable, and a lot of compilers does that. So again, this is what I just told you. Memoize the table. So the data stored in the memoization table is its non-terminal comma position, and then you just return the length of the match and the AST. So these two techniques are really the fundamental techniques you need to add in your standard conventional compiler construction to get this sort of intelligence we see in editors. Okay, for example, VS Code extensions. And LSP events, just to summarize what LSP events are, there is did open, which gives the LSP a complete text buffer, you parse it, and then you have did change event, which gives you just the text edit, right? So now here you can either completely parse it, but let's say if you want to have that incremental optimization in place, you just reparse incrementally just using the text edits, and all other events are there. And the publish diagnostics, you publish the diagnostics while parsing and name resolving. So that's how it works. Now, I want to talk about WIDL compilers, which is basically a compiler we developed for our own smart contract development and offer it to developers so that their smart contract development experience is really smooth. Okay, and I have tried it, and I can seriously vouch that the compiler techniques in blockchain space can do wonders. It can really provide that kind of productivity which developer needs. Now, again, so what's a blockchain? I mean, a better answer has been given by Saurav sir. So I just have to recap it. So a blockchain is a distributed ledger with growing list of records that are securely linked via cryptographic hashes. But for our context, blockchain is just an execution runtime which executes something called as smart contracts. Okay, and so now what is this thing called a smart contract? Smart contract is a piece of code which is agreed upon by the parties involved and is uploaded on the blockchain. Okay, and now anyone can submit transactions which call one of the exposed methods from this smart contract. That's what in a nutshell smart contract and blockchain execution semantics is. Okay. So for a much more technical point of view, smart contracts are compiled WASM binaries basically. Okay, and the blockchain just has embedded runtime to execute those binaries. What's a WebAssembly? WebAssembly is a binary instruction format to an stack-based virtual machine, and so it can be targeted by a whole lot of languages. Specifically, LLVM targets WebAssembly, so all the languages which compiles to LLVM or targets LLVM IR can be compiled to WASM, and WASM is just a binary instruction format which can be executed in a runtime, either in browser or in as an independent runtime, like WASMer, WASMtime, and so on. This is again what I just told. WASM memory model, it has some imported function and has some exported functions. So exported functions are the functions you can call from the runtime, from outside. And that's where WIDL comes into picture. So smart contracts are just WASM binaries which export functions that can be called from host based on client request. Okay. For example, this is one kind of a specification of a smart contract, and these methods it should expose. Okay. I'm just moving a bit fast, short of time. It can be, so the methods can be called by clients, what we call as clients. Now, clients can be either a crypto wallet, okay? It can be a decentralized application, okay? Or it can be a CLI, which is provided by the developer. So it can be any client which needs to interact with the blockchain and execute a smart contract, okay? Again, this is, yeah, so that's where WIDL comes into picture. So WIDL is an ideal to specify smart contract exported functions and their typed signatures, okay? And the general idea is you specify your interface and then you can generate client bindings or server bindings for it. For example, this is an example of WIDL syntax, and you just specify your interface, you can define record types, enum types, aliases, and so on. And you define this interface, and now just defining this interface will be open. So let's say anyone wants to write a smart contract based on this specification. You just generate Rust client bindings for it. So this is Rust client binding. It generates native Rust types and the traits and so on. It moves forward and even implements that trait by some struct, which and leaves unimplemented methods. So you have got the interface. You just have to put the business logic in, and you are done with your smart contract. It's for a dApp developer, it means that he can generate client bindings and get native TypeScript types. For example, the details it generated. So this is a real generated code, okay? It generated the native TypeScript code. It even generated the Zord schema for validation. This is the whole validation code. Basically, the programmer doesn't need to think about serializing it, deserializing the result, validating the data types, nothing of that sort. It just gets a native function like API which they can directly interact with, which is really, I mean, the holy grail of programming languages, right? And other compiler uses, as you may all know, is also that people wants to write secure smart contracts, and that's where they are saying that, okay, we are going to write our own programming languages to provide type systems like that, to provide security like that. And again, so let's say Ethereum did Solidity, Dime has Move, Internet company has Motoko. They can target either their own VMs or they can target a general bytecode instruction format like WASM. For example, Solidity targets EVM or can target WASM. Mostly people are now inclined towards targeting WASM. Okay, now last bit, it was in my proposal, so I included it in slides. Why Rust? So the WIDL is written in Rust. So why Rust is a good language for compilers. Just last 2 slides, and I want to argue a few things. So first of all, first reason is that the first software which was written in Rust is itself. It's a bootstrap compiler, and it's 97% written in itself. Okay, and being with its ownership borrow checker, it means that Rust has implemented one of the most complicated compilers out there. So Rust is probably good for implementing compilers, but even more, Rust plus Wasm ecosystem is just awesome. Okay, and in future, I am really sure that Wasm will become a standard target for a lot of softwares, not just Linux, Windows, Mac OS, but also Wasm people would be targeting. Okay, and Rust is really good because it doesn't have that sort of crazy runtime magic like garbage collection. It provides a fine-grained control over the memory. Wasm memory as of now is not automatically managed, helps you a lot in that front. Again, Google is making some strides in that space with Wasm GC and so on. And so, yeah, thank you.
Nice talk, Bhavya. I think it comes directly from a practitioner, which is quite useful. I will take some questions from the audience. Please raise your.
Are there any commercially available incremental compilers that you talked about? Store the thing and then add only the new
Yes.
tokens. Is it available?
Yeah, it's implemented. I mean, one of the language server implementations which I know personally is Rust Analyzer. So it's a LSP for Rust, which implements this incremental parsing approach. It's even in TypeScript compilers. Okay, one thing I forgot to note is that there are languages who have different LSP implementation and different CLI implementation. And so they sort of diverges. So you have to have this first day decision to make it common. Yeah, make it like error tolerant parsing so that your CLI and LSP is in perfect sync. Yeah. For example, TypeScript did that. Yeah.
Yeah. So I probably missed it in the initial part of your presentation, but are you using top-down parsing or bottom-up parsing?
Top-down recursive descent parsing.
Recursive descent.
Recursive descent
because
parsing.
bottom-up parsing has had this, whatever you said, ever since the first Yak version was introduced. There's an error token. You put that error token and it does exactly what you said. So this has been there for ages. I mean, ever since the very first instance of Yak was announced. So I thought I'll just point this out.
No, so does it every time generate a AST?
Yes. Yes, you can construct a AST. See, the point is there's a missing token. You want a placeholder.
Right.
So error token gives you, so you can use error as a valid token in your Yak script.
Okay.
Okay. And you can construct an AST. You can construct an AST or you can throw an error. It's up to you.
Okay.
But the point is you can proceed even in the presence of, in fact, error recovery has been a very interesting mechanism of Yak. Of course, recursive descent has easier error recovery,
exactly.
better diagnostics.
Right.
But
it's much more flexible. Yeah.
Building AST with error tokens has been there in Yak, in bottom-up parsing since the beginning.
Yeah, so this even incremental techniques which I talk goes way back in 90s or so. So
yeah,
it's old. Yeah.
I did my master's project in 1988 on incremental parsing. So yes, it did exist at that time.
Yeah. But given that, it's very less explored then.
Hello, sir. Great talk.
Thank you.
You use Rust in your WIDL compiler?
Yes, yes.
To overcome the errors thrown by the borrow checker, do you use RC and ARC in the code base?
No.
So
it's purely using generational indexes we do the stuff. So that means that we completely bypass the problem by using generational indexes and keeping our whole state in a global array, in a global context array. So we don't face any ownership problems there. No RC. RC has downsides. Yeah.
Hey, I heard you mention about some language extensions for the blockchain context, right? Can you be more specific what actually you extended? What are the kind of constructs that were more useful for the blockchain use cases?
No, can
No, I think I heard you say that there were some specific extensions to the language using your compiler you made for the blockchain use case, right? Maybe tunneling directly into the blockchain runtime. So can you give one instance where you actually did that?
No. So the thing is that we didn't extend the runtime. It's just that if developers are supposed to be writing this code manually, they may not even have the expertise to write the code, because a lot of time runtime details are exposed from these SDKs. So what we do is we give programmers their own native language APIs, and WIDL generates underneath all the code, runtime dirty code, right? Boilerplate code is required to interact with the blockchain and the runtime.
Okay. Okay.
Yeah. So
Okay. Thank you.
it's a productivity tool basically. Yeah.